give you some what is an identity? If you got two things, so if you have two things and you're saying they're identical, what does that mean? They're the same. Very much the same. Exactly the same, actually. Not just similar, but the same. Good. And in math, we indicate that by the equal sign. Whenever you see an equal sign, it is telling you the two sides are the same thing. Okay. Sometimes we get it where there's a place like there's an x value that makes them the same thing, but in this case we want to think that when we have that equal sign, it's saying they really are the same thing. The other part we get out of this is that when we graph mathematically, if we graph both sides, what do we see? We see the same graph. So we're going to also be able to verify some of these by graphing it and say, yeah, they're the same graph. One graph's on top of the other. They're identities. They're exactly the same. So there's some basic ones we're going to use, and then we use those to sort of prove that the other ones that they give us are identities. So here's the reciprocal identities. So we've got cosecant is 1 over sine, secant is 1 over cosine, and cotangent is 1 over tangent. So that's one way we can think of them. So those are reciprocal identities. We won't prove those. We could, I guess we could graph them, but they're more, they're a definition. That's what these things are. There's also the quotient trig functions. So tangent could also be thought of as sine over cosine, and cotangent could be thought of as cosine over sine. So we define sort of tangent separately what it is, right? It's the opposite over adjacent. We could think of it that way, but we'd also think of it as sine over cosine. And what you're going to see is one of the techniques we use to verify things is we turn all the trig functions into their equivalent sine and cosine form. So at least that's the way I do it. I don't know about other. It's not really. I don't really have a lot of fun with this, so to me it's not like I spent. But I have colleagues that I've worked with that they love this stuff. I just sort of like it a little. But we'll turn everything to sine and cosine. We'll manipulate them until they look like the other side, and that's what we're doing today. So it's mostly manipulating things. There's a couple more. There's even and odd identities. So if we have the sign of negative x, that's the same thing as the negative sign of x. So it means that these two are identical whether you put the negative inside or the negative outside. Remember, the negative inside is a reflection. That's the x. That's making the x. I think that's a reflection around the y-axis, if I get that right. And the negative on the outside is putting the negatives on the y, so it's a reflection about the x-axis. So if you reflect about the x-axis and you reflect around the y-axis, you get the same curve. That's what that's saying. Cosine is sort of a little different. Is the negative x actually gives you a reflection back to cosine x. So cosine x. So that's if you were flip it over the y-axis, you can't tell the difference because it's symmetric. It's an even function, is what that's saying. Sine is an odd function. Tangent also is an odd function. So that's what those things, even and odd identities. And then we have the Pythagorean identities, which we will find useful. Anytime you see a 1 in some of these things, you're going to say, hey, maybe I could replace that with sine squared plus cosine squared. These second two really come from just taking the first one, and I'll show you, you don't have to necessarily memorize them, but if you take this first one, and if you divide all of these by cosine squared, and can we do that? We have an equation. We do the same thing to both sides. Yes, we can do. That's what's nice about math. You can almost do anything you want as long as you do it to both sides, right? And so what's this? Sine squared is actually tangent, right? This is tangent squared x. Cosine squared divided by cosine squared, that's 1. Same thing divided by itself. And then 1 over cosine, if we remember, that's going to be give us our secant squared x, and that's just this bottom one. The middle one comes from dividing by sine squared x. If you did that, you could see, oh, you'd get that one. So those last two I don't always try to memorize. I just remember sine squared plus cosine squared equals 1. If I can remember that one, which I typically do, it's kind of like the Pythagorean, right? A squared plus b squared equals c squared. And if we think it is a triangle from the unit circle, the other two sort of follow, and I don't necessarily remember them, but I can create them. Okay, let me divide it by cosine squared. That's what I get. Divided by sine squared, I can get it. But I'll look for the final exam. We do give you formulas because we're going to be dealing a lot with formulas. I'll get that to you. It might, on the last test, did we have formulas? Yeah, it might be the same one, but I'll look ahead one way or another to find out what it is so that you can start using it while you do the homework. Because then you know, hey, I'm going to have these, or I'm not going to have these, and so you kind of know which ones you have to remember, which ones you can use. But I think we give you these anyway, but we'll see. So now we're right into the lesson, and it's just going to be basically a few techniques. We've got 4 examples. We're going to work through them together. Verify means sort of to prove that these two things are equal. So I'm going to show you from the start one way we can prove that two things are equal. I think it's a good proof, is graphically. We can graph the left side and graph the right side. If the graphs are identical, then they're equal. That's always a good place to start. Sometimes we give you a function, like we give you one side and we ask you it's going to simplify to something. If you graph it first, a lot of times you might be able to recognize what it simplifies into. I think we do that a little bit further down in one of the lessons. But anyway, let me go ahead and pull up the calculator. Sine, secant, cotangent. So what we do is we're going to graph. Let me get rid of this stuff, this stuff, this stuff. Did I say it? So it's a sine of x. I forgot. Secant? Secant. And again, we don't have a nice secant function here, but what is secant? Secant is 1 over cosine. So I'll put that in there as 1 divided by cosine x, parentheses, parentheses, and then it was times cotangent. Again, I don't have a cotangent, but I could put that in as 1 over tangent. 1 divided by tangent x, that's my cotangent. So I put that in. And then what was the other side? Just 1. And then I'm going to show you, there's something called, let's talk a little bit. You can be in either radian or degrees for this, for what we're doing next, because it's going to graph them the same way. I'm in radians, which probably is good for most of what we're going to do. There's also something called a zoom trig, and so that kind of fits the window for trig functions. It's a good one to use for these, so it kind of just gives probably a good 3. There's the first curve, and there's the second curve. Did you see that? It went so quick. One was blue, and then the other was red. Are they right on top of each other? Yeah. Okay. We graphically proved it. Okay, done. Let's move on. No, we'll show you how to do it analytically. But that's the first proof. They are the same curve. And where are we? There we go. Come back to this thing. Okay, so the process I use is I'm going to take the more complicated side and try to make it look like the less complicated side. That's what they say. And yeah, so we're going to take and we're going to kind of manipulate the left side until we get it equal to 1. And we'll see on the other ones we kind of do that too. And what I do mean by manipulate is I'm going to change everything into terms of sine or cosine, and then we'll see how things cancel out. So sine theta is already sine theta, so that one I don't have to do anything with. This middle one is secant theta. What is secant theta? 1 over cosine. Cotangent we could write it as 1 over tangent, but again, I want sine and cosine. It's cosine over sine. Good. Cosine theta or x over sine theta. Actually, I'm going to get away from the x. What I'm going to do is I'm just kind of working the left side. I'm not working this as an equation. I'm going to work the left side until I get it to be 1, right? And so sine theta, think of it as sine theta over 1. We just multiply the tops. So sine theta times cosine theta in the top. Cosine theta times sine theta in the bottom. Whoa, that's kind of cool. Because what happens to cosine divided by cosine? That's 1, right? What happens to sine divided by sine? That's 1. We're done. So this is a verification because we used identities that are known, that are sort of defined, turning them into sine and cosine, simplifying, and we ended up with 1. And that's what we were looking for. So we could put the check mark, we verified it. So that's what they mean by verify. You'll see these don't really make very good multiple choice type questions because you have to just kind of go through it. And mostly what you want to think of, this is a practice to get you working with these identities for when we go to solve equations, which are in the next lessons. So this lesson by itself is not something, it's just really practice to get you ready for those next ones. Okay, and sometimes math is like that. Why are we doing this? You know, it's not necessary to solve a problem, but to build a skill that gets us there. Any of you guys seen the Karate Kid movie? He's about the same age. He's no longer, he's karate grandpa, right? So it's a long time ago. But I love that movie where he's going to learn karate, and Mr. Miyagi just has him washing his car, waxing the car, wax on, wax off, painting the fence, doing all this stuff. He said, I came to learn karate and you're not teaching me anything. But he was learning skills that he was going to need. That's what we're doing today. We're painting the fence. Okay. This one, we've got two sides that are pretty complicated, so we could actually start with either one. So what we're going to do is do the same process, but we're going to try to get one to look like the other. Now, that's the idea. So you start with one side until it looks like the other. Sometimes it's hard to know because, right, we're dealing with a unit circle type thing. We're dealing with trig functions that repeat. And sometimes we just go circles and we're not getting to where we want to go. So what we do is we cheat a little bit. We start with the other side and we start working it. And we meet in the middle. And then we erase that stuff and it makes it look like we started and ended. But sometimes we'll work them from both sides. But the key is to go here. So I've got a secant and a cosine, a tangent and a sine. Which side do you want to start with? Anybody have a preference? Which one? Left side. Okay, might as well. If we don't know, just start with the left. So again, what we're going to do is we're going to take everything on the left and turn it into either sine or cosine. Secant is 1 over cosine. X. Cosine's already cosine. I'll put it over 1 though, so I'm going to indicate that I'm starting with the left side. And I want to make it look like this. So I've got to get it so it's tangent times sine. Sometimes we just don't know where to go. I mean, we could graph these again, and we would see that they are one graph. That might be helpful. Any suggestions? What should I do? Got them both in terms of sine and cosine. We could do that, but that's sort of like we'll save that for a last resort. Although you might want to do it for a first resort because that might give you an idea. What do we have on this left side? We've got a fraction minus something. If we're going to get common denominators so we can make them one thing, because on the other side it's all multiplied. And again, yeah, we could kind of cheat and do it, but we'll see how this is going to be helpful. So we want cosine as our common denominator, so this becomes cosine x, cosine x. We're getting a common denominator. And so that becomes 1 over cosine minus cosine squared on top, right? That's cosine times cosine. Now we put the, let me just, when we say cosine squared x, when you go to graph this, the way you're going to need to graph it is cosine x squared on the outside. You don't actually do cosine squared and then the x on your calculator, because your calculator won't know what that means. So it's just a shorthand that we put the square on the cosine itself. Does that help? Okay, so when you get there, divided by cosine. Now they have a common denominator, and again we're trying to work just the left side, so we can actually subtract this. So when we have a common denominator, we put it over that common denominator, and it's 1 minus cosine squared. Oh, that seems familiar. What is 1 minus cosine squared? It's what? It's an identity, sort of, but it's not the one that was given. We were given this identity. Let me change colors. We were given sine squared x plus cosine squared x equals 1. But what they've done is it's that identity, but manipulated again. So you also want to be able to, whenever you have cosine squared, 1 minus cosine squared, right? We could subtract the cosine squared here. It's another version of the Pythagorean identity. 1 minus cosine squared x. So we've got that, and we look over here. So this is, it's not cheating, but who cares if we cheat anyway. But we see a sine squared, we see a sine over there. So if we replace that with a sine squared x, we're getting closer to what we want, right? Because we need a sine. All we had was cosines. So what we're going to do is we're going to replace this with sine squared over cosine. And again, we're looking, okay, but this is not sine squared x, it's just sine. Oh, but tangent. Now I'm kind of stuck maybe. And I'll take your advice, Quinn. We're going to now just kind of, okay, let's cheat a little bit. Let's turn this side to sines and cosines. So tangent is sine x over cosine x, sine times sine. Oh, look at, if I break this sine squared into sine times sine, which I can do, right? I'm not really going to put equals, but I could rewrite this, let me bring it up here, as sine x times sine x, and I could put it over cosine x, and then what's sine squared over cosine? There's my tangent times sine x. Boom, I'm done. So notice how I to kind of figure out what I needed to do, I did work with the right side to say, okay, where's the step? How do I get there? Because we're using identities, but it's which ones do I use? Which ones, what pieces are going to need there? So we sort of do back and forth, and then again for the proof we clean it up and we say, no, we didn't do that. We just went straight through. We knew what we were doing all along. But we get lost, and that helps us. We come back a little bit. Does that help? Does that make sense? Sort of? Yes, sir. Yes, we could have started with the right side and done the same thing until we got equal to the left side, and sometimes one way will be easier than the other. It might be more direct. In fact, I think if we did that, it might, because notice if we turn this, we could then turn this into sine squared, and it's over a cosine. We would have had to separate it into two fractions, and that might have been harder to do. We would have had to do the other substitution. Either way, I think this is one, if I'm working it, I'm actually going to go from both ends until I get, and then the middle is kind of, that's easier to work with. I know what I need to do once I get to the middle, and then So we could go either way, but I think I would get stuck either way without working both sides. And that's what my teacher would always get on me, so I got good at erasing my cheats, or putting that on another piece of paper and then making it look like I knew exactly what I was doing all along. But, that's how it works. I had another teacher, they were fine with this, so they supported it. But it's giving us, because this is in itself is not a big deal. There's no competitions for who can verify the trig functions the most eloquently or the fastest, but they're just practice so that we can solve equations when we get to those next ones. So I think it's a great idea. Work both of them. Here's another one. Now again, it's equal to 1, so we see that's a very simple side. So it's natural to start with the left side, and what we're trying to do is get it equal to 1. Again, if we graph it, we'll see that they are equal. And whenever we have something equal to 1, what does that put off in your mind? Which identity are we probably going to be using? One of those Pythagorean ones, because sine squared plus cosine squared equals 1. So we're probably going to get there. And again, that's probably the direct one we're going to use, but we'll see. So again, first step, write everything in terms of sine and cosine. So secant is 1 over cosine, right? I'm going to use x instead of t's because my t's look like plus signs and I get confused. And then this is over cosine x. Minus tangent is sine over cosine. And actually, just to make it so it's, it's a fraction over a fraction, I'm going to write the denominator here, cosine of x, as cosine x over 1. So I got I got a fraction in the top, fraction in the bottom, and then we're going to divide fractions. To me, it makes it a little easier to line everything up. So we'll go with tangent being sine x over cosine x divided by cotangent. Cotangent is the reverse, so that's cosine x over sine x. Okay. And then when you've got a complex fraction, you've got a fraction divided by a fraction, fraction over a fraction, we're going to rewrite it as a fraction divided by the fraction. So I'm going to say this is, the numerator is 1 over cosine x. And then when we multiply, so it's cosine over 1, but how do we multiply fractions? Or sorry, how do we divide fractions? We flip it and multiply, right? So if we have cosine over 1, doesn't that become 1 over cosine? Not theta. Let's stick with x. So notice this comes from taking the reciprocal of the denominator and multiplying. Is that okay? Anyone have questions? Because if you don't get that part, then nothing else makes sense. So that's how we always deal with them. We got a fraction over a fraction. We'll do it over here. So this is now minus sine x over cosine x. So that's the numerator. I'm going to multiply by the reciprocal of the denominator, which is sine x over cosine x. Okay, so the first one becomes 1 over cosine squared x. This one, sine times sine, so we get sine squared over cosine squared x. We have a common denominator, which is kind of nice, right? So we can combine these fractions that are being subtracted. Let me take it up here. So we get 1 minus sine squared over cosine squared x. Remember, our goal is that we need to make it equal to 1. Fractions are equal to 1 whenever the numerator and denominator is the same. What do you see that we could do here? What other substitution, what other identity can we invoke and bring in? Very good. So we could actually do either one, right? So we could either replace the numerator. We could say from the Pythagorean theorem, this is cosine squared, right? Sine squared. We just did this last time, plus cosine squared x equals 1. Subtract sine from both sides, you get that cosine squared x equals 1 minus sine squared x. So we could replace the top with cosine squared x over cosine squared x, which is equal to 1. Right? Same thing in the top as the bottom. You also could have replaced the bottom if you wanted. Maybe you would say, oh, cosine squared, that's 1 over sine squared, but we would have gotten, so we replace 1 minus sine squared, and in the numerator we had 1 minus sine squared, and those cancel out, and those give us 1. So we could make either, we could use the identity either way. Okay, so that's what's nice about this, is we have some control over which identities we apply. Yours might be different than your neighbor's, but you could both be correct. That's always nice. Questions on that one? Okay, good. Now, this one, let me get this out of the way. It's a little bit harder because we're just asked to rewrite it in terms of secant squared. Or, sorry, give away the answer. In terms of secant. We don't know if it's going to be secant squared or 2 secant or 3. We don't know what exactly it's going to be, but it's only going to be something with secant. But we remember, what is secant? Secant is 1 over cosine. So we're going to do something with these and try to get it to be like 1 over cosine probably, and then switch it over to cosecant. Okay. So we're starting off, and again, we could graph these. It might help a little bit. There's one that we have in our other class that says in terms of sine or cosine, and so you know, graphing helps, but it's not going to help too much here. So anyone have a suggestion? We've got 1 over 1 minus sine x plus 1 over 1 plus sine x. Bless you. So we got 2 fractions being added. How do we add fractions? Common denominators. Good. So this is, we're going to be invoking a lot of fraction skills. And we might not be the best at fractions. I hear that like 4 out of 3 people are bad at fractions. Did you get that one? 4 out of 3. So there's only 3 people, but 4 of them. Okay. We're all bad at fractions. Okay. Not as bad as that joke, but oh, okay. Here we go. So our common denominator is actually 1 minus sine x times 1 plus sine x, because they're already factored, so we need one of each. So the one on the left, we're going to multiply it by the one on the right. So this is going to be 1 plus sine x that we multiply by. And to do that, whatever we do to the denominator, since we don't have an equal sign, we have to do the same thing to the numerator. Okay, so getting common denominators, we multiply the denominator and the numerator by the same amount. Over here, we're going to multiply by 1 minus sine x. And notice the denominators now will be the same thing. So we multiply the top up here, 1 minus sine x. Okay. So in the numerator, we're just this here we're multiplying by 1. So we've got 1 plus sine x. We've got a plus sign here, so that comes there. This one is going to be 1 minus sine x. This may be kind of good. We see the sine x's are canceling out, right? We got a 2 there. What do we get in the denominator? Now this is always the part, well, let me just write it. 1 plus sine x times 1 minus sine x. And sometimes it's hard to know what should we FOIL that out, or should we just leave it? But since we're trying to get it in terms of secant, if we don't do anything with it, it's always going to be sine, right? So we kind of get to work at these. So let's try to simplify it as much as we can. So here we have a positive sine x and a negative sine x, so that becomes 0. We have a 1 plus 1. So in the numerator, we end up with 2. And then let's FOIL out the denominator and see if it helps us. So we get 1 times 1, right? 1 times 1 is 1. We get 1 times negative sine, so that's negative sine x. We get sine x times 1, positive sine x, so we get a plus sine x. Those are going to cancel. And then at the very end, we get a sine x, a positive times a negative, so that's a negative sine squared x. We okay with that so far? Okay, so we just FOILed out. Negative sine x cancels with sine x, that becomes 0. So I'm going to go up here. This leaves us with 2 in the top. 1 minus, right, there's, yeah, 1 minus sine squared x. We're looking, we want secant. Secant is a cosine. Oh, can we turn that into some kind of a cosine thing? 1 minus sine x equals cosine x, right? That's a Pythagorean, that's that manipulated Pythagorean identity. Instead of redoing it, I'll just say here it is, right? So we did it here. So remember those Pythagorean identities. Oops, I went the wrong way. Here we are. So I'm going to replace this with the identity cosine squared x. So I got 2 over cosine squared x. What else could I rewrite that as? I could also call that 2 secant, right? Because secant is 1 over cosine. Which also means that 1 over cosine squared is secant. So I can just kind of jump through the hoops and rewrite this as 2 secant squared x. And that would be my answer. So I have rewritten it in terms of a secant. And again, why did I do it? Because they asked me to, and it's just kind of manipulate to try to get it into that form. Again, when we go down into the next sections, we're going to be solving trigonometric equations, and we're going to need to manipulate them algebraically. And so this is really just a skill building, getting some experience with manipulating sines and cosines and rewriting things. Questions on that one? Okay. That's it.